always add something. There's no semicolon here. Keep in mind. That's the first problem I saw from a couple people. Second, interestingly, so I'm not sure which language uses this kind of syntax. So input, when you are putting the input and output or declare input-output signals, quite a few of you guys use the parentheses here, like A, B, C, like this. Okay, so there's no parentheses, keep in mind, there's no parentheses. And there is a semicolon after that, okay? For hierarchical modeling method, the same gate only needs one model, only needs one module, okay? For example, the OR gate for hierarchical design, it's like a library. In your drawer or library, it's called OR gate. For example, OR gate. And since you have a module of OR gate, right? You have this module somewhere and N module. Blah blah blah. Okay? You just need to do it once. So that OR gate can be reused for millions of times, doesn't matter. So you don't have to have two different OR gates in the sub as a sub module for your top module. So you only need a one OR gate, one AND gate, and so when you instantiate it in the top, we don't have ports for top, okay? When you instantiate in top, you do OR gate, give it a name, OR gate 1, right? And do the connections. And then you can instantiate this for one more time, but still the same OR gate. OR gate 2. So this can be reused for millions of times. The same thing as electric VLSI. Just keep that in your mind. Thinking about the layout or the lab one from last Thursday, I think. So once you have that DAC module in your library on the left-hand side, remember there are several different views. For example, you have a R2R DAC. Okay, in that library, there's a little like global sign, whatever, in there as a library component. And then you remember you have two different views that you created. One is a schematic view. Remember in electric VLSI, it's R2R DAC. I think it's .sch or something. Sometimes I got confused with Eagle PCB, but it's a schematic view, right? Another one is R2R. Remember, you click view, create icon view, so it directly creates a little icon inside that schematic view. But however, it's also creating an icon view for you in the library as well. So it is R2R DAC dot. What's the extension for that? I don't know, something, okay, icon view, for example. And this week, on Thursday, you are going to do another one, so there are totally 3 different views for one cell. It's not just for VLSI, electric VLSI, also for Cadence in the future. It's just industry standard. So there will be another view called R2R DAC dot lay, I think. So it's a layout view, which is just basically masks. Okay, it's drawing of the masks to fabricate all the chips. So there's 3 different views. For example, you have this DAC icon. Remember how we used it in the simulation? You open up another sim, right? It's a sim R2R DAC dot sch, for example. That's a schematic. It's a sim simulation schematic. And we open up this simulation schematic, we directly drag, we click on this icon on the left-hand side of the library, remember? We click and drag and drop it into this schematic for the simulation. And so we drag it into the schematic views, and we can connect all the voltage sources and spice code to it to run the simulations. So my question is, can you drag two? Can you drag two of these icons into the schematic? Yes. Can you drag 1 billion of them into this schematic? Yeah, possibly if you have the time. But there will be some automation. That's why we need the EDA tools. So it's can pull all these components into your design automatically. Like all these Verilog tools are pulling all these TSMC standard cell libraries, all these little D flip-flops and mux cells that were pre-designed by TSMC that I can directly use in your design. So just write your Verilog code and some of the scripts, it will directly pull them from the schematic, from the libraries and put in your design. Same concept. So this is the icon, right? This is the icon. We can reuse it for so many times. It's a very similar design concept, even though they are using different technologies. But they are both being used. They are both being used for the chip design, even though it's the FPGA, but it's still on the chip, right? Same idea. You have one icon, even though it's not really an icon, but it's the module, right? Here's the module. You can consider it as an icon. So you can drag and drop in here for multiple times. The same concept. All right. Another problem here. Structural. Okay, a lot of people are forgetting the name. This is problem number 4, actually. This isn't problem number 3, it's problem number 4. For structural, like you are instantiating this one, or, so it's OR logic, right? OR logic. So OR is the keyword in structural. It's a keyword. So for OR, a lot of you guys forgot the name, so you need a name for it, like OR gate 1. And start with output, keep in mind, out, and in 1, and in 2. Okay, you cannot miss any of this component. So the first one has to be the output. I have probably 3 of you guys, 3 to 5 of you guys had that issue. Okay, got the input and output flipped. So keep in mind, output comes first, and then followed by inputs. Does that matter the order for these 2 inputs? Doesn't matter. They're just equivalent inputs. So name, don't forget the name. That's another common problem. Number 5, for behavioral, for the behavioral, since it's not the module itself is not a top. It's a sub module. Sometimes you got mixed with because both of them have the initial begin. They are thinking about, is this a simulation? Are we going to put stimuli in it to give a signal to the inputs? No, it's just it's a sub module. It's not a top. It's not a simulation. It's just one of the 3 modeling methods: behavioral, structure, and data flow. Right? It's just one of the 3 methods. There are still sub modules. Behavioral. Initial is a keyword. If you have a begin, you have to wrap it with end. Keep in mind, begin, end. Okay. Q is 0. Keep in mind, when you are modeling the submodule, when we are giving an initial result to here, is because we didn't have any initial input at the very beginning, so we give some output value at the very beginning, so it's not showing a uncertainty when you run the simulation. Probably already saw that kind of simulation results. Some of them are showing 1 zeros, but at the very beginning it may show this 2.5. It's not 0, not 5. It's not 0, not 1. It's just in the middle, so it's unknown, right? To avoid that, you can directly give initial output at the very beginning before you have any inputs, because behavioral, behavioral modeling methods is triggered by the the signal lines in the sensitivity list. If nothing of the signal lines on the list got changed, there won't be any outputs. It's waiting for some signal changes. So in that case, we are trying to give an initial value to it to avoid this unknown signal at the beginning. So these are usually outputs, keep in mind. You don't need to give every single signal a value at the very beginning. Doesn't really required. It's not required. Another thing you need to know, if you only have one line of code for initial, begin end is not required. It's only required if you have more than one lines. Because sometimes you'll see initial and Q equals 0. That's it. Okay? It doesn't have to have begin and end if there's just one line of code. All right. I don't have other issues. Any questions from you guys? Yeah, I'm gonna give you another quiz like this next time, so hopefully everyone can get 100 on it. Okay. Let's move to the next topic. Super important ones. FPGA connections on the hot wire. Did you bring your board with you guys today?
Yeah.
Good? I can give you one. Yeah, subscribe. Yeah, just bring the board every time in the class or lab. You have it?
No, I didn't. I started my car that day.
Okay. So there will be some really simple FPGA it's called emulation because it's running on the board. We'll talk about that once these two guys come. So let's look at. Let's wait a little bit. You know, still on the way. Okay, take a look at the plan for this week. So on Thursday, there's another new tutorial covers new materials. So there will be a lot of homework assignments. That's why I'm giving you guys a break, sort of break on Tuesday. But still have to come for quiz 4. It's just gonna be just a quiz, very quick quiz on the FPGA board. So bring your board over on Tuesday next week. But for the rest of the time, I'm not going to, cover new things on that day. So we're not having another new assignment after that. Okay, so I'll give you a brief break on that, so you can work on homework 3, which is due Wednesday, one day after that. But starting from Thursday, we'll have new materials to be covered, right? Memory cells, pretty important. For the labs, this afternoon, right?
Yeah.
We'll be mainly on the board. It's going to be programming the board either through the bit file and the bin file. So the bin file will be stored in the memory, on-chip memory, use a SPI communication protocol. So when you unplug your USB, you still have the program stored somewhere. Okay, so you are not losing your program. Because the current FPGA, you unplug it, it's gone. So I have to store it somewhere. Right? Okay. Yeah, let's talk about some of the calculations first before we move on to the board constraint files. So understand the hardware of the board. So there's some of the data types we need to cover. Fixed point, floating point. So fixed point is pretty simple. The UQ 16.16 standard, just keep 16 bits on the left hand side of the point and another 16 bits on the right hand side of the point. Let's zoom in here. Okay, it's very straightforward. So for example, 14.125. Okay, convert it to binary first and then expand it into 16 bits on both sides. Any question on this? Very simple, right? 16 bits on both sides. This is hex. So 4 binary digits for each digit here. So 4 times 4 will be 16. Okay? So for a fixed point, Q format or Q notation, it's a unsigned Q notation. 16.16 will be just 16 binary points on both sides. That's it. Very simple. For signed, you just flip the first bit. If it's a negative number, just flip it, change it to 1. Okay? If it asks you to create a Q15 dot format, which means there's no bits after the dot, so it's losing the fractional part of it. So just to have 15 bits over here and use MSB as a sign. Okay? Pretty simple. And for floating point, need some calculations, but still very simple. Okay, we don't really worry about all the following 3 different formats because it's just very similar to the first one. The first one is the easiest one. If we know how to do that, it's gonna be just repeating. So the key things we need to know is the exponent bias is 15. Right? So the reason we need that is sometimes the number is less than 1. Let's take a look. I mean, it's confusing just by talking about it. Let's look at one of the examples. So the way to convert the number into its floating point using the half precision, it's just the name of the precision, half precision format, right? You can see there are 4 different formats defined by the IEEE 754 standard. So we're only looking at the first format. It's called half precision format. So how do we convert it into this floating point? So it's being represented by S, E, and F. So how do we create S, E, and F in your computer system? So keep in mind, the goal is to convert it into a fractional number into a format that is easier for the computer to store and run all these computations. It's actually not exactly the real number. It's just trying to fake it into a different format so the computer is easier for the computer to store. So if you look at this one, 14.125 as a decimal number, you convert into to its binary format, it's going to be this 111.0.001, right? And then the first thing you want to do is shift it and only leave one digit in front of the point. So it's going to be 1.110001. So in that case, the point was shifted to the left by 3 times. So that means the number is being divided by 8. Does that make sense? Let's review the logic stuff, okay? Are you still familiar with this kind of things?
Yes.
From binary?
Yes.
So like 125 as a, for example, this is a decimal number, right?
Yeah.
So originally the point is over here. The point. If I divide by 10, so it's moving the point to the left, so it's become 12.5. If I divide it by 100, so it's moving the point to the left by 2 digits, it's 1.25. Same for binary numbers. If I have 1101, it's a binary number divided by 2. It's 2 based. If I divide it by 2, the point was here. I divide by 2, it becomes 110.1. So the binary number divided by 2, you shift the point to the left by 1 digit. You times 2, you shift the digit to the point to the right by one digit. So 1101 point is a binary number times 2 becomes 11010, right? So it's adding a 0, adding a trailing 0 to that original number if you times 2. So 1101 point, okay, divided by 4. So you are moving this digit to the left by twice, by 2 digits, 11.01. So that's how that works. If we come back to here, the binary number, if I move the point to the left by 3 digits, 1, 2, 3, so it's basically dividing this number by 8. So I need to multiply 8 back to recover it, right? So in that case, this number, the number 3 over here, will be used to be added to 15, which is a bias. You see the half precision has a bias, which is 15. You just add to it. Just add to it. So it becomes 18. Okay? So 18 equals 10010. So the question is, why do we need a bias? Because sometimes this number can be negative whenever this number is lower than 1. You know what I mean?
Yeah.
So let me show you one number here. Like 0.00111, okay? So for this number, how do we shift it? So we want to shift this one. So this equals, we want to shift it here. Just have 1 digit on the left-hand side of the point. So we're going to shift it to the right by 3 times. So it becomes 1.11. So this has to multiply it by what? Okay, so this becomes negative. So you need a bias. Otherwise, you have another issue, right? You want to always have positive number in your binary number. So the memories are not able to store a sign. You just have to tell the computer system what is a sign. The digital memories are only storing 1 and zeros. They're just transistors, either 1 and 0, 5 volts or the ground, but no signs. Just have to tell the computer system, okay, this is a negative number. So that's how we fake it, using some sort of transformation. All right, so but this time, for this case, it's a positive number. That's why it's getting 15 plus 3 results in 18, and this is your E. That's the E part of the floating point number. Okay, so for the E part, you let's just keep it here for now. And then for the fractional part is basically just this fractional part. You don't have to change it. You don't have to multiply it by anything else. It's just simply a fractional part of the number. And but take a look at it. For half precision format, for floating point format, we need 10 bits for the fractional. So if it's less than 10 bits, you just add trailing zeros. If it's more than 10 bits, you just trim it. So if you look at this fractional number here, we just got here, is less than 10 bits or more than 10 bits? It's less than 10 bits. So we want to add how many trailing zeros? 4 trailing zeros. So eventually it becomes this. Okay, it becomes this guy. 110001 and 4 trailing zeros. So that's the fractional part. So eventually this number, whatever the original number is, it becomes a combination of the binary numbers formed by consists of S, E, and F. You just simply put them together. So E, we already calculated. E is over here, and F is over here. So you can see E is placed here, F is placed here, and S is just a sign. Okay, if it's 0, if it's positive, it's gonna be a 0. If it's negative, it will be a 1. So the way to do that is over here. It's a -1's 0th power. Okay, so apparently if it's a positive number, it has to be a 0. If it's a negative number, it has to be a 1. Right? So this original number can be represented by S, C, and F combined, and that becomes a floating point number using the half precision format. And then you convert it into group them into 4 digits, into 4s. Eventually, it becomes a hex number like this. 4B10 is a floating point number for 14.125. So you're faking it, right? You're telling computer, hey, if you see a number like this, you just convert it back. So you should know that it's actually 14.125. Okay, that's how we store a fractional number in the computer system, by using a floating point format. So eventually this number simply becomes a 16-bit binary number stored in the memory, which is doable, right? So for the negative numbers, you can also convert it into the half precision format of the floating point. So if it's a negative number, definitely put a 1 in the front, and then just do the following procedure as what we did over here. Convert it to its E and F accordingly, and then put them together like this. Okay. For this one, it's a little bit different because it's less than 1. So you can imagine it has to be 15 minus something, because E will be negative. So this time it's a -1, -3. Okay, so that's it. We don't need to go too deep. There's no reason to practice all the other precisions and just having super long numbers. We don't have to do that, but just understand what's really going on for the floating point numbers being stored in the computer system. So there's a calculator online that I can use for some of the calculations. Okay, it shows you the link to it. For ASCII code, it's just a table. It's very important. 8 bits numbers or 2 nibbles, right? We have, for example, LSB, MSB. So these are LSBs and these are MSBs, right? For example, let's take a look at D. So D is 4-4, right? A, lowercase a, is 6-1. Does that make sense? Yeah. So A over here is a 6 and 1. So that's the ASCII code for this number. It's going to be very important for us to program the data transmission using USBs and the parity code generators later on. I think it's Thursday. So we need to know the ASCII code. So there's a table. You can download the table from Google. You can look at all the ASCII code for every single character on the keyboard. And next, okay, so for the signal lines that are more than 1 bits, when you declare them, you have a bracket in front of the variable when you declare them. Okay, when you use them or access to the single bits inside that, longer binary number, you put a number after that variable with a bracket. So you can use 3 to 0 shows MSB and LSB. You can also use 0 to 7, but usually we don't do that. But it doesn't matter. But eventually what's really happening is if you declare this guy this way, it just starts from 0 to 7, from left to right. So just keep in mind that no matter how you declare it either from 3 to 0, 7 to 0, or 0 to 7, like this guy, it always starting from the left. So for example, if I directly just look at this number, okay? I'm gonna make a snapshot over here. It's really simple, okay? If I do this, okay, if I'm giving res3, which is a output, and assign this one to res3. What's happening there? What's going on? So
yeah, so basically as it runs, it's assigning res3 to be equal to num1. So it's like, I guess, copying the value of it.
yes, but looking at the when we declare it over here, right? So this guy has 7 to 0, right? 7 to 0, and this one has 0 to 7. Like I said, it's always starting from the left. So what's really happening is you are giving the MSB or the, so it's basically doing this. Give it to what?
Oh, it's really basically going 7 is equal to 0 of the, yeah, it's res3 of 0 is equal to num of 7.
Okay.
And that would be 1.
That's how that works. If you just do one line of assignment like this, it's gonna basically the same thing as these. Okay? It might be useful in the future at a point, but just let you know how that works. Just keep in mind that it's always working from left to right. So whenever you are doing this, it's basically having a memory space storing the numbers from 0 to 7 from left to right. Okay? So for the rest, it's just very simple. I mean, just using the same concept, and it's asking you to run the simulation to verify this idea over here. Lookup tables, we don't have a simulation for this example. It's not that important. And then there are two different combinational logic design that require you to implement it onto the FPGA board. So that's where I want to talk about the constraint files a little bit. So this time I'm asking you guys to use vert new in Vim. Use colon vert. Vert means it's going to display a window on the left hand side vertically, like this, with a line. You can see this dashed line in the middle, so Vim can directly split the two windows. Even though GVim is really not that advanced, but this kind of feature is important, especially for digital design. The reason for that is a lot of times you cannot remember all the name of the ports. I mean, 2 modules is fine. What about 5 modules? What about like 100 modules? 100 modules we are not opening every single one at a time with a Vim window, but usually it's very common. When I was doing some of the design with more than like 5 modules, I was able to open up every single one in Vim, but getting the split window, and I can use Control W, so that's how you switch the cursor in between those modules. It's really handy. you got five modules open up at the same time, for example, and you are able to see every single port from every single module. When you declare making connections, you know what's really going on from other modules. So let's try to do this time, even though it's only 2 modules. So it's going to be colon vert new, right? It's creating a new file, and just name it something.v, right? So it's going to open up a new file over here, and can use Control W. Keep in mind Control W to switch that cursor in between the windows, and you can use Vim commands in every single window individually. It's not affecting other windows. Okay. So for example, this one open up a sub module at the top. But let's just look at the circuit first. It's really simple. So circuit home alarm. So it's assuming that every signal line is connected to an alarm. For example, this is attached to window 1, window 2, door 1, door 2. Okay, either one has a signal got triggered. It's sending a 1 to this signal line. Okay, it's the OR gate. So the thing is, whenever there's a 1, it's gonna output a 1. So it doesn't matter which one got turned on. As long as there's a 1, at least the 1 signal line got a 1 as an input, the output of the OR gate becomes a 1. Okay, so in that case, you have to enable this AND gate by turning on this M. You have to turn it on to enable this AND gate. So whenever there's a 1 comes in, A becomes a 1. Okay, that's an alarm, super simple alarm system. But because the first time we are using FPGA to implement it, so still probably requires some time for guys to figure this out. Think about that. How do we design it on the FPGA? Look at the hardware resources on the FPGA. What do you have? So inputs, can LEDs be inputs?
No.
Yes, if you have a light sensor, but we don't.
Yeah.
Can switch be an input? Yes. Yeah. Okay. So can LED be an output? Yes. It turned on, you see it, right? It's the output. So in that case, we can use switch as the inputs and LED as the output. So you can imagine A can be connected to one LED. Doesn't matter which LED you want to use, but connect to one LED. And M to be connected to one of the switches. You probably need 5 switches. M to be connected to one of the switches. You turn it on, you enable the system. You turn it off, no matter which one got triggered, A won't be turned on. So that's what you want to verify on the FPGA board. So turn on M, system enable, and any 1 or 2 or 3 or 4, doesn't matter. At least one of them is on. The switches over here is on. You should have this LED on. Okay, that's it. Just to verify it using a very quick demo video and upload it to your YouTube account or anywhere else. Include a link into your report. So that's one of the examples, and that's another example. So this is how you you are using a video, but showing some pictures in the report. It's also helpful. It's not required if you have a video. Okay, this is another one. It's a parking system. Oh, digital safe. Oh, it's a password. One quick question from logic. Anything XOR 0 is what?
Is they both 0? Then it's 0.
Yeah, let's try it. Let's go through all these possibilities. Or let's say A XOR 0 is what?
That's just A.
Yeah. A XOR 1 is
0.
A not. Why is that? Let's take examples. If A 0, 0x0 is what? 0. If A is 1, 1 XOR 0 is what? 1. Because they're different.
Yeah.
Right? So 1 XOR 0 is 1. So which means no matter what A A XOR 0 becomes A. So you can verify this in the same way. So A XOR 1 is going to be A naught. It's getting flipped. Okay. Let's come back. Doing the quiz on this? No, thank you.
Yeah.
Take it easy, Dr. Lee. Let's take a look at this one, okay? It's a password, okay? So I think P0, let's say P0, P1, P2, P3 are a password you store in a register data type at the very beginning, right? And then you're using your switches, try to match this password. So the thing is, if they are the same, it's an XOR gate, right? It's an XOR gate. So if the switch input, you are using the switch, try to explore all these password combinations, okay, eventually you get the right one, for example, and all of them, all the S values match the pre-stored P password values in the register in your FPGA. So they're all the same, which means it's outputting zeros. Because XOR gate, if you are getting the same inputs, XOR gates are outputting zeros, right? So getting zeros. And you're getting inverted, so you're getting ones. So it has to be all ones in order to have this AND gate to output a 1. So eventually this is a 1. So you can use the LED to show that if this is the 1. If this LED is on, which means the password is correct. Okay? Don't create like 10 bits. Okay? Or asking for extension for the homework. It's not a good excuse. Yeah?
And a lot of gates.
Mm-hmm. Any question on this logic? Easy, right? XOR gates. Try to match. Okay, here's the logic. That's a pre-stored password. You can use a parameter data type to pre-store that parameter here. And use FPGA to do it. Car parking logic. Car parking logic. There are 3 spots on the parking lot, S1, S0, S1, S2, assuming that there's a sort of light sensor on the top of the parking spot, detecting if there's a car occupying that spot, right? So if the sensors are outputting zeros, you want to output a 0, both zeros, because so C1 and C0 is a count. That's why it's using C, because I think it's trying to have a binary count. So if all of the signals are outputting zeros, that means the optical sensors are detecting that car. It doesn't matter. You are probably thinking it should give a 1. Doesn't matter. It's just inverting it. It's okay. So depending on the transistor's connection, okay, pulling out, pulling down, doesn't matter. So for example, we know that if the sensor is outputting a 0, it's detecting the car presenting in the parking spot, and the count should be 0 because they're all occupied. Okay, if there's 1, like this spot is not taken, right? It's not taken, and it should count a 1. So no matter which one is not taken, you should always output a 1. See? 1, 1, 1. Okay? So count is 1. C1, C0 is a 2-digit binary number. It's 1, 1, 1. And this is 2. This is 2. 2. 3. Okay, that's a truth table. And you can look at every input to find out the SOP, right? Sum of product. So you are looking at the ones, 1, 2, 3, 4, okay, to write down the SOP for C0 and C1. It's already given, so you are not really doing anything from the truth table. So directly use it. And here's the code, and here's the top module. I'm going to explain what's really going on for the top after the break. So we have these calculations for the data formats, and we have the tasks for the digital systems on the FPGA. That's all the tasks for homework 2. It's really clear on that. Any question on this? Okay, so for this week, keep in mind all the ones we just went through are homework 2, and there's the homework 3, which is due next Wednesday, but I'm giving you the time to work on it on Tuesday next week as well. But doesn't mean that you want to start working on it on Tuesday. It's giving you more time. Okay, just giving you more time on Tuesday. So on Tuesday we are not covering new things, just a quiz, very quick quiz on the FPGA. And for the lab this week, this afternoon, all right, it's mainly just on the FPGA, and I think there are several tasks, so we'll talk about it in a bit over here, like regarding the mux and the running LEDs. Okay, we'll talk about this a little bit after the break. Let's take a 5 minutes break. Come back at 9 probably. Yeah, come back at 9.
Sounds good. Just like you do the same thing.
All right. So go to the website. Let's start programming one simple gate on your board for the rest of the class. So make sure you have no problem on it on that. This is the lab, right? Let's go back to the homework tutorial. Here, homework 2. Scroll down to let's see, find out the file here. So add the constraint file Basys3 underscore master.xdc by downloading it from here. So unclick it. So it's going to download the file to a computer and unzip it. Unzip it so it will be a .xdc file. So in your Vivado, you can right-click the constraints and add it to the design. Okay, so use Vim and the vert new something, create a 2 split windows, a top module and sub module like this. The code is already provided, just type it in. That's the OR logic, that's brackets, you know, accessing all the digits in this binary number, 4-bit binary number. So once you have that constraint file downloaded, let me know. I'm gonna show you here really quick. So I right click and open it in Vim. So it looks like this, constraint files. So it defines all the connections to the hardware on the board. Super important. You can see here, clock, CLK is a keyword. If you are using FPGA as a top module. Oh, one more concept here need to talk about really quick. Remember when we were doing lab 1 or homework 1, there was a little digital design with ports, okay? And then we place this thing under a top module. Okay, so the top module doesn't have a port, remember? Because we are directly injecting signals into and probe it. So we're injecting signal into it and probe it like this. That's for simulation. So for FPGA, it's going to be different. You got a chip, it's the same module design, doesn't matter. It could be the same Verilog code, for example, the AND gate or the home alarm system. So for the top module for the FPGA, it's going to be different. So for the top module here for the hardware design, the FPGA becomes the top. So actually the board on your hand is the top. So whatever you guys are going to do is to make the connections between your sub module to the available resources on the board. like switches, LEDs. Okay, so switches as the input, you need to make the connections. LED as output, you need to make the connections. Have to specify that in order to have the inputs and output as a response from the board. So the top module now becomes FPGA. So now we come back to the code, and you can see SW. You can see SW lowercase. It's case sensitive. Keep in mind, every single year I teach this class, I have issues with that. Students are stuck into the errors. It's gonna figure that out because sometimes I use uppercase LEDs, sometimes I use lowercase LEDs, depending on your constraint file. So this is the one I downloaded from this website. So let me know it's lowercase or uppercase for the LEDs. You couldn't even find LEDs. It's here. LED 0, LED 1, LED 2, LED 3, 4, until 7. Oh, 15, sorry, 15. So you have 16 LEDs, and it's lowercase LED. It's case sensitive. So if it's lowercase LEDs in your constraint file, when you are coding it up as a top, you need lowercase LED. So the top module for the FPGA, this LED doesn't have a number of ports over here, number of pins. It's by default we are using all of the 16 pins. But in here, you can define just the LSB of the LED to be used. See, this is really weird, right? 0 colon 0, which means it's just 0. So basically, we only declare LED 0 to be used, but there are 15 LEDs, which is fine. Okay, you're just using the rightmost LED on the right hand side, which is LSB of the LED, as an indicator. So switches, also you have 16 switches, but you're only using five of them as inputs, because 4 of them are signals and 1 of them is enable switch. So SW, if you come back to the constraint file, SW is a keyword and it's lowercase. So for the sub module, you can see S has 4 pins, so that's why 4 pins connect to the 4 switches. 4 pins, 4 switches, connections. And M connect to the 5th pin of the switch. And A connected to the LED. And yeah, that's it. Let's make this work before you leave of the class, okay? So in the lab this afternoon we have more similar projects to work on, but let's get this done before you leave. Work on the home alarm system, okay? I think this is one of the assignments, so it's not, I think section 5, task 3, I think, yeah. Section 7, home alarm system, digital safety system, parking system. Repeat the work, include the snapshots of the code, simulation results, and FPGA demo video. So when you are done, take some pictures and record a video, upload to your YouTube channel, put in the report. Oh, you guys use TikTok right now, okay? TikTok. Red Note. TikTok refugees. You Chinese can afford groceries?